everyone. Welcome back to the deep dive. One of the things I love about our listeners is that you guys are all about getting to the heart of things, grasping those big key ideas without getting lost in the weeds. And today we're diving into something that might seem a little out there at first.
Out there.
Yeah, we're talking about quantum physics. But believe me, it's not as abstract or irrelevant as it might seem. This stuff is actually becoming more and more crucial to our daily lives and the technologies we use. And to guide us through this, we're going to be leaning on the brilliant physicist Brian Cox and his really insightful 22-minute explanation of quantum physics on big thinking.
Oh, excellent choice.
Yeah.
Cox is great.
Yeah, he's really good at breaking things down. So our goal today, right, is to really understand those core principles of quantum mechanics. Like, what are they really about? And more importantly, why are they important? And not just in some, theoretical physics lab, but how do they actually impact us in the real world, in the world we live in? Because here's the thing. A lot of people, when they hear quantum physics, they think, okay, that's all about atoms and particles, right? Tiny stuff. How does that affect me? But the truth is, the quantum technologies that are emerging, well, they have the potential to change everything.
Absolutely. You hit the nail on the head. It's tempting to think of quantum physics as this very niche, almost esoteric field, right? Something that's happening at scales so small that it has no bearing on our everyday experiences. But as we see these technologies like quantum computers starting to emerge, it becomes undeniable that these quantum principles, well, they're not just theoretical curiosities, they're actually fundamental to the way the universe operates at its most basic level. And the more we delve into these technologies, the more understanding these principles becomes absolutely essential.
Yeah, and that's a good point to jump off from. So, one of the things that Cox emphasizes right off the bat is that there aren't different rules for the subatomic world and the world the world we experience every day. He says, and I'm quoting him here, there aren't different rules of the game in the subatomic world and the world that we observe. And I think that's a bit of a head scratcher, right?
It is.
Because we tend to think of the quantum realm as this almost magical place with totally different laws than our everyday reality. But he's saying, no, the rules are the same. The strangeness or the weirdness that we associate with quantum mechanics, it's not because the rules are different. It's because the rules are applied at a scale that our brains just aren't used to dealing with.
Right. Our common sense, our intuitions, they're all built upon our experiences in the macroscopic world. And those experiences are fundamentally shaped by the averaged out behavior of trillions upon trillions of quantum interactions happening at a level we can't directly perceive.
So it's like, if you look at a smooth surface, it seems, well, smooth, right?
Right.
But then you look at it under a microscope and you see all these bumps and valleys. So our reality is kind of like that, except the bumps and valleys are these strange quantum phenomena that are happening all the time, but we only see the smoothed out, averaged out version.
Exactly. It's a brilliant analogy. And this inherent strangeness, I think, naturally leads to the question, why should anyone who isn't a physicist bother trying to understand these quantum mysteries?
Yeah.
What's the point if it all seems so removed from our daily lives?
And Cox, in his video, he touches on a couple of really interesting points that I think are worth exploring. Firstly, he points out that even physicists themselves, even the experts in the field, haven't completely agreed on what quantum theory actually tells us about the fundamental nature of reality. Like, what does it actually mean about the universe we live in? There's still a lot of debate and discussion about the interpretation of quantum mechanics. And to me, that in itself is a pretty compelling reason to try and understand the basics.
I completely agree. If even the brightest minds are still grappling with the philosophical implications of quantum theory, that tells us there's something deeply profound and potentially transformative about these ideas. And the way we learn about these ideas is changing as well. Cox talks about how, when he was a student, the traditional approach to teaching quantum mechanics was to kind of retrace the historical development of the field.
So you'd start with the photoelectric effect and then move on to Bohr's model of the atom and all that.
Exactly. All the early models, all the revisions, all the initial struggles that physicists went through to make sense of it all. It starts to feel very much like a historical journey through all the dead ends and breakthroughs.
I can see how that could get pretty overwhelming.
It can be. But the more modern pedagogical approach, as Cox highlights, is to actually start with our current best understanding of the theory. It's like saying, look, here's what we think we know about how the quantum world works based on the mountains of evidence we've gathered. And to build this understanding, he suggests focusing on a fundamental property of particles called spin, which leads us naturally to this concept of a qubit.
Okay, so let's talk about qubits, because I think this is where it starts to get really interesting for a lot of people. Cox uses a really helpful analogy of a classical coin to explain this. A coin, right, it can be heads or tails. It's a very definite state. But then when we enter the quantum realm, we encounter this mind-bending concept of superposition. So with a qubit, which is like a quantum version of coin, it's not just heads or tails. It can be both heads and tails at the same time, or as Cox puts it, any combination in between. And that's not just because we don't know which state it's in. It's fundamentally different.
That's a crucial point. In classical probability, the probabilities we use are a reflection of our lack of knowledge about the system. Like if you're trying to predict the weather and you say there's a 30% chance of rain, that's because we don't have perfect information about every single factor that influences the weather. But if we did, in theory, we could predict it with 100% certainty. But in the quantum world, it's not like that. The probabilities are inherent to the system itself. It's not that we don't know if the qubit is heads or tails. It's that it's genuinely both at the same time until we try to measure it. And then when we measure it, it collapses into one of those definite states.
So to be clear, it's not like a coin that's spinning in the air where we don't know if it's going to land on heads or tails. A qubit in superposition is actually in both states simultaneously. It's not just a lack of knowledge on our part, it's a fundamental property of the quantum world.
That's right. And this brings us to what Cox calls the one experiment, which encapsulates all the core properties of the quantum world. And he really recommends diving into Feynman's lectures on this. The double-slit experiment. It's a classic experiment that beautifully demonstrates this wave-particle duality. So imagine this setup. We have an electron gun that fires electrons one at a time towards a barrier with two narrow slits cut into it. And then behind the barrier, we have a screen that detects where the electrons land.
Okay, I'm picturing it. So if electrons were just particles, like tiny marbles, we'd expect to see two distinct bands on the screen, right? Like one band behind each slit where the electrons went through.
That's exactly what our intuition would tell us. But that's not what happens. Instead, what we see on the screen is an interference pattern.
What do you mean by interference pattern?
So an interference pattern is a pattern of bright and dark stripes, and it's something you typically observe when waves, like water waves or light waves, pass through two slits. What happens is that the waves from each slit, they interact with each other. When two crests of a wave meet, they add up and create a bigger wave. That's a bright stripe. And when a crest meets a trough, they cancel each other out. That's a dark stripe. So in this experiment, the electrons are somehow behaving like waves and interfering with each other.
So we're saying these tiny little electrons, these particles, are also acting like waves. Okay, that's already pretty wild. But it gets even weirder, right?
It does. The real head-scratcher is that this interference pattern, it doesn't go away even when you fire the electrons one at a time. So there's only one electron going through the apparatus at any given moment.
So what's it interfering with? It's interfering with itself. It's as if the electron is going through both slits at the same time and interfering with itself. It's a very counterintuitive idea, but as Cox points out, many physicists believe that this is literally what's happening. And this has profound implications for our understanding of reality. It suggests that reality at this level is not a fixed objective thing that exists independently of observation. It's more like a spectrum of possibilities. And the act of observing is what forces it to collapse into one specific outcome.
So the universe is basically saying, I'm not going to decide which slit the electron goes through until someone looks. It's wild. So how do we even begin to make sense of this mathematically? Well, Feynman, he had a very elegant way of describing this using complex numbers. So instead of just working with regular numbers that represent quantities like 1, 2, 3, and so on, complex numbers have this additional element to them that allows them to represent both a magnitude and a phase. It's kind of like thinking of each possible path the electron could take as having a little clock associated with it. And as the electron travels along that path, the hand on the clock rotates, and the angle of the hand represents the phase of the electron's wave function along that path.
I'm trying to wrap my head around this. So each possible path the electron could take, even like the absurd ones going to the Andromeda galaxy and back, has its own little clock. And we add up all these clocks to get the probability of the electron ending up at a particular point on the screen.
Exactly. It's a way of accounting for all the possible ways the electron's wave can interfere with itself.
But here's the thing. This mathematical framework, it gives us incredibly accurate predictions that match experimental results. But there's still this fundamental question: is this just a useful mathematical tool? Or does it literally describe what's happening? Does the electron really travel along all these paths simultaneously?
It's a deep philosophical question that physicists are still debating. But as Cox notes, many are now leaning towards the idea that this is actually a literal description of reality. And I think it's an important point to emphasize. It's not just that we don't know which path the electron takes, it's that it takes all of them at once. And this, I think, leads us to a really exciting area of research and development, quantum technologies. And specifically quantum computers.
Because all this weirdness, this quantum behavior, it's not just theoretical, it's actually becoming the basis for these amazing technologies that are emerging. And quantum computers, well, they're like the poster child for this.
Exactly. And as we talked about earlier, quantum computers, they're built on qubits, which can be in a superposition of states, both 0 and 1 at the same time. So they can explore many possibilities simultaneously, unlike classical computers that have to go through each possibility one at a time. And that's one of the reasons why quantum computers have the potential to be so much more powerful.
So this idea that things can be in multiple states at once, it's not just this weird quirk of the subatomic world, it's actually being exploited to build computers that can tackle problems that are currently impossible for our classical computers.
That's exactly it. And to add to that, there's this other fascinating quantum phenomenon, entanglement.
Ah, yes. Spooky action at a distance.
Right. Cox explains this using the example of two electrons prepared in a special linked state called a Bell state. In this state, these two electrons are connected in such a way that their spins are correlated. So for instance, one might be spin up and the other spin down. But we don't know which one is which until we measure it. And this correlation, it's not just a statistical thing.
What do you mean?
I mean, it's not just like, flipping two coins where there's a 50-50 chance that one will be heads and the other tails. These electrons are connected in a much deeper way. And here's the crazy part. When you separate these entangled electrons, even by vast distances like sending one to Pluto and keeping the other one here on Earth, if you measure the spin of one, you instantly know the spin of the other, no matter how far apart they are.
Okay, so that's where the spooky action at a distance comes in.
Yes, and this really bothered Einstein because it seemed to violate the idea that nothing can travel faster than light. He thought there must be some hidden variable, some underlying mechanism that we just weren't aware of that was explaining this correlation.
So he didn't believe in the spookiness.
Right. But experiments have shown that entanglement is a real phenomenon, and there aren't any hidden variables. It's a fundamental property of the quantum world. And when you start entangling multiple qubits together, along with their ability to be in superposition, that's when the computational power of a quantum computer really starts to explode.
So it's not just about qubits being able to be in two states at once, it's also about how they're connected through this spooky action.
Exactly. And as Cox points out, the number of possible configurations that a system of qubits can be in, it grows exponentially with the number of qubits. So with just a few hundred qubits, the number of possible states becomes larger than the number of atoms in the observable universe.
It's mind-boggling. So quantum computers, they're not just faster versions of our current computers. They're fundamentally different. They use these principles of superposition and entanglement to explore vast numbers of possibilities simultaneously. And that's why there's so much excitement and investment in this field. Companies like Google, Microsoft, IBM, they're all pouring resources into developing quantum computers.
And it's not hard to see why. Imagine the potential. Designing new drugs and materials, creating unbreakable encryption, developing artificial intelligence that can truly think and learn like humans, and who knows what else. We're really just scratching the surface of what these technologies might be capable of.
So to sum up, I think we've gone on quite a journey here.
We have.
We've explored the strange world of quantum mechanics with concepts like superposition, where things can be in multiple states at once, and the idea that probabilities are inherent to the system itself. We've delved into the mind-bending double-slit experiment, which shows us the wave-particle duality of quantum objects. And we've touched on the mysteries of entanglement, that spooky connection between particles that seems to defy our intuitive understanding of space and time.
And what's particularly exciting is that all this strangeness, all these seemingly abstract ideas, they're not just theoretical anymore. They're the driving force behind these incredible technologies that are emerging. And as we learn more about the quantum world and how to manipulate it, who knows what amazing discoveries and breakthroughs we might make.
It really makes you wonder, If a single electron can explore all these possible paths at the same time, what happens when we start to control and manipulate systems of billions of entangled particles? What kind of reality-bending technologies might we be able to create? And what will that tell us about the true nature of the universe and our place in it? That's something for all of us to ponder.
Absolutely. And I encourage everyone listening to delve a little deeper into these topics, to explore the resources that are available online and in libraries. It's a fascinating journey that will challenge your assumptions and expand your understanding of the universe we inhabit.
Thanks for joining us today on the Deep Dive. Until next time, keep exploring, keep questioning, and keep diving deep.
Bye, everyone.
See ya!